Okay, so I would like to first of all start off the spring 2021 with a big welcome to the introduction of metallography and microstructural interpretation. It has been a goal of mine to get a class like this started in order to emphasize the importance of this particular technique and um, in any form of engineering, really, to solve issues or create new materials, to just better understand materials on a microstructural level. As we move forward, just to touch bases, I know that we covered a little bit of this in the lab through our intro session, but I want to be able to provide methodology and knowledge for proper sample preparation using standard metallographic procedures. And when I say standard metallographic procedures, I'm essentially combining in a package sample selection, the orientation, sectioning, the mounting grinding process, etching, and the photographic documentation that you'll be utilizing to complete the metallography for any type of material system. And in the process of doing photographic documentation, you'll be able to take advantage of some software programs to help you identify ASTM grain size standard, ASTM grain size using ASTM grain size standards, performing measurements. So if you're working with coated components or you're looking at powder, then you can perform measurements using the software programs. And then porosity comes in handy. There are some instances where a certain amount of porosity is allowable for certain castings, aluminum castings, for instance. But it can be detrimental if you have too much porosity within a sample. So you're able to do any type of software analysis using those programs. And then on top of that, how would you put that down onto paper or a PowerPoint or speech when you go to a conference or anything of that, to where we're going to look at now, how do you improve the technical and verbal written skills? Mechanical engineers, if you're trying to relay information to a metallurgist on a certain design, how do you relay that information to them? Okay, and then metallurgists, if you're trying to, let's say a comparative study, you're trying to do vendor A versus vendor B, how would you relay the information that vendor B is better than A, so that way whoever your client is in procurement, who has no background in engineering, would be able to make the correct decision to either save the company money or choose the better material. And then, of course, being in the labs, we got to be professional and take into consideration the safety measures that we'll need in these laboratories. It's not your typical chemistry lab, because we do have equipment in there that can potentially harm you. So there are some things that separate a metallurgy lab or metallographic lab versus a chemistry lab. So what is metallography? Well, I look at it as an art, but it's also the science of preparing and interpreting, analyzing microstructures for metals and or other material systems by means of microscopy. And that microscopy could be either your light microscopes, scanning electron microscopes, more than anything else. And if anybody ever questioned why is this technique important, well, it's going to essentially tell you the structure of the material. It's going to give you the history of the material. How was it made? So the type of the material, the distribution and shape of phases. You're looking at how it was fabricated. Was this something that was hot worked, cold rolled, cast? Was this additive manufacturing, powder metallurgy? And for those that have gone through the metallurgy department, you'll see that there's a correlation between a microstructure and its mechanical properties. And I'm hoping that I can help relay that information to the other engineering backgrounds that we have taking this course. It also gives you a sense of failure modes and also imperfections within the material. Imperfections can be anything from inclusions, lack of fusion if you're talking welds, just maybe the wrong grain size for the wrong application. And what industries use this method for evaluation? Well, if you think about it, when it comes to engineering, there would be no such thing as engineering without metallurgy, right? So metallography being a technique through metallurgy, you're looking at automotive, aerospace, aviation, the oil and gas, energy sectors, construction, medical, manufacturing, and litigation. So when we're going through practical interpretation, we got to realize that and this might be handy when it comes to having to start doing some definitions, but pure metals consist of one phase. Okay, so that's a pure metal. When you start alloying, now you can exhibit several phases, but you can also have a single phase structure. Okay, and in those phases and structure, you're going to see that a phase is physically uniform throughout the entirety of the component in the material. Okay, it has the same crystallographic structure and properties, but it might not be chemically the same. And you see that a lot when it comes to cast products. Okay, and of course we'll get into what all this means when we start looking at the visual imagery of what coring is in cast structures. Structures can be made up of several phases. For instance, for those that know steel very well, you have ferrite and cementite, which in combination creates perlite. So with the lab safety, I know that you guys will be taking a EH&S class in order to be in the labs, and they're structured heavily on the chemistry aspects. So I'm just gonna run through these slides and just pick out a couple of the important factors of what separates really the metallurgy lab from a chemistry lab. So to kind of give you a quick overview, all metallographic labs are relatively safe environments, but with the lack of maybe discipline or lack of experience in a lab, you can run into many potential hazards if you become too complacent. Something, I don't need to work on this too much, or it's not going to hurt me, and then all of a sudden that's the time that an accident happens. So just some topics to cover: laboratory standards, some SDS sheets, the importance of being professional and practicing etiquette in the lab, looking at some of the equipment and various substances that you'll be dealing with in the laboratories. So some quick references that I've posted onto Blackboard are the following. And you're looking at ASTM E2014. It's the standard guide on metallographic laboratory safety. Then OSHA is the occupational exposure to hazardous chemicals in laboratories. And also OSHA's hazard communication standard. Okay, so in those documents that I had posted on Blackboard, those are the only sections I'm looking for you to read and kind of be familiar with the content within that section. I believe the OSHA standard I put up on Blackboard is a 52-page document, but I'm not looking for you to look at all 52 pages. You can if you want, but the only one you'll be responsible for are the two that are listed here, which would be 29 CFR 1910-1450 and the 29 CFR 1910-1200. When we're looking at SDS sheets, every lab has to have a safety data sheet. They used to be known as material safety data sheets back in the days, and that switched a couple of years back to just safety data sheets. And it's useful when you're encountering chemicals for the first time. And the reason why is because they list all your physical and chemical characteristics. So your flammability, explosive properties, effects on human health, adverse reactions if it's mixed with any of the other chemicals or materials, how to handle them, controlling exposure, emergency and first aid procedures, and of course, in case of an accident, let's say spill containment. The thing about it is anybody working in the lab has a legal right to know about the hazards they face and ways that you can protect yourselves from those hazards. So having these safety data sheets listing all of that will provide you that right to know. Okay, so that's why it's important for various health reasons. Not everybody in the world is identical. Some people might have allergic reactions. You might be pregnant. You might have other health conditions that these chemicals or exposure to certain items in the lab might have an adverse reaction to yourself. So when we're looking at a laboratory scale, the way OSHA defines a laboratory scale is the use of the containers designed and easily and safely manipulated by one person. So what that means is if you are on an industrial application, obviously, it's going to take a ton of people to move and use large quantities of just a few chemicals. Our labs, industrial applications such as like extractive metallurgy would use a lot of the higher concentrations or higher quantities of the same chemical. Let's say Freeport-McMoRan, our local copper refinery here. They use large quantities of sulfuric acid. Okay, our labs typically use a wide variety of chemicals because we're in the realm of using a wide variety of materials, and not all materials react the same to a specific chemical. But we don't need thousands upon thousands of gallons of sulfuric acid the way the copper refinery industry uses it to refine copper. So in this case, we have a wide variety of chemicals, but in much smaller quantities. Those quantities are anything from a liter below. So when you're looking at the general categories of what's going on in the lab, we talk about physical hazards. You have your fire, you have explosion and reactivity, health, of course, anything inhalation, swallowing, or skin or eye contact. Now, depending on your exposure, you can have acute chemical exposure, which gives you a short-term health problem. Let's say a rash, headache, dizziness, where typically if you step away and you go outside, get some fresh air, you wash your hands, that stuff will go away. But then you have the chemicals that over longer periods of time, or some chemicals are just that dangerous that just small amounts of overexposure can lead to serious, more long-term health problems where it damages your internal organs, reproductive, where you can have reproductive issues, cause cancer, and or even death. So what do we do in the lab? I mean, we are in college. I don't think any of us have a fifth grade mentality. So, it's obviously going to be a lot of safety. And so what I'm going to do is kind of just skip through. But first, one of the things that we have on our end is a chemical hygiene plan. And this plan is to protect any of employees, students, from health hazards. And those are typically done when you're looking at your standard operating procedures. So when you're working in the lab, you'll be, especially when signing up for Open Lab, you'll have the opportunity to create a standard operating procedure for the whatever methodology you're going to be going in the lab for. And that helps right there protect you, because you're going to be writing that up so everybody knows your plan. You know how to measure the exposure of your hazardous substances. So using proper PPE, looking at using the proper equipment, like fume hoods, training programs. So as we mentioned, that everybody's going to go through an equipment training. That's part of our hygiene plan. Need for any type of medical examinations, consultations as a result of any type of accidental injuries. And then, of course, just any other additional protection if you were working with something that was very hazardous within the lab. But everything is pretty much controlled. Let's say additional protection for employees. You know, we will be using hydrofluoric acid, which is bad stuff. And we'll discuss more on the health hazards that come with hydrofluoric. But we do have the proper PPE of handling hydrofluoric, where you have to take the extra step to make sure you're safe when using that particular acid. General lab safety rules. You know, all of these bullet points on here are pretty much self-explanatory. We all know not to eat or drink in the lab because of all the things that could possibly happen. You're going to realize that you know, if you're a fanatic and you love drinking water, well, what else is the color of water in the lab? Just about everything. Acetone, acids, bases, you know, other solvents, ethanol. So you could always pick up the wrong bottle if somebody doesn't label it correctly. So one of the key things I would like to get out of this, and I feel is important, is to handle everything as if it's dangerous. You don't know what you're handling, you know, and if you take caution, even when handling ethanol, methanol, acetone, or nitric acid, if you handle it carefully, then you're already taking steps to being safe in the lab. The next one that I feel is important in this also would be not only utilizing proper protective equipment such as fume hoods and PPE, but to wash your hands. And it's not this is not a COVID related tip. This is more of washing your hands before and after lab work, because when you put the gloves on, you're touching items, right? And the nitrile gloves protect you for a certain amount of time. So if you've been wearing these gloves for 2 or 3 hours, you do have the propensity of having some of these chemicals in low quantities penetrate into, you know, through the gloves. They can get into your hands. And if you're going around touching stuff with these gloves, you might be protecting yourself, but you're not protecting others. And the next one would be to clean up after yourself. I say this, and this is probably my strongest one, is when you're in the lab, you have to clean up after yourselves. It's just good for the lab. It helps everybody move along with their lab, so that the next group that comes in, they're not spending their lab time cleaning up a mess that was created by you and wasting, you know, it's just it's a good way to make a lot of people mad. So my big rule is to clean up after yourself. Looking at lab practices, safe work habits, housekeeping and cleanliness. If you keep it neat, it's going to be easy to work in. You can get, you know, promote yourself some safe working habits. If it's sloppy, that's going to be a big disaster. So, you know, like I said, a lot of this stuff is chemical based. You'll get a lot of the touch on this when EH&S goes through their lab safety training. Key source of information on SDS sheets. Once again, kind of reiteration of what I discussed before. It has hazardous ingredients, physical chemical characteristics, physical health hazards, how to take precaution on protecting yourselves, storage and handling procedures. Not everything can be stored. A lot of the times it's only make fresh and dispose afterwards. And then what happens if you do get nitric acid spilled on you? So a little cartoon is knowing and doing are not the same thing. You might know what to do, but if you don't practice what you preach, you're going to get hurt. Okay. And as you can see, that guy right there, he just says, "Oh, I know all about safety. That's why I never get hurt." But he's about to fall into a trap, right? Let's look at chemical spills. Once again, just something small and less dangerous is something that a trained person can do in the lab. So after you've gone through EH&S training and some of working in the lab, you're going to see that the quantity of the chemicals you're going to be working with are likely less than 100 milliliters. So that would be considered a small, less dangerous spill. A larger, more dangerous spill, something that might require hazardous materials experts, is something where if you drop and you broke a bottle of nitric acid, and that's all over the floor. Or I don't know if you would ever be playing with mercury, definitely not on this shift, but that would be something where you would have the chemical experts come in and handle that mess. But either case, either scenario, all labs would have a list of phone numbers that you can call in the event of an emergency. So 5 steps of handling a chemical spill in short, it's just to be sure that you can walk into the area safely. Identify the spill. So if the person created a spill and they say, "Hey, I dropped a bottle of nitric acid," first thing is it safe? And then the person already identified the spill as nitric acid. Then you have to choose a cleanup method, treat the spill, and then restore the area back to its useful nature. And of course, kind of self-explanatory, you need to wear the proper PPE when cleaning up the spill. So what does that mean? To choose a method for cleaning the spill, well, there's 2 different methods that you can use. One is called sorption. You're using pads or other forms that can absorb the spill, and which then you will dispose of those pads. Of course, you have to make sure that whatever you're cleaning up is not reactive with the sorbent, which is your pads. And then the next one is chemical neutralization. So if you spill an acid, you have to use a caustic, a base. Baking powder, sodium bicarbonate are 2 caustics that you can use to help neutralize an acid. And of course, if you spill a base, you would use an acid to neutralize it. Reducing agents in order to neutralize oxidizers, and vice versa, oxidizers to neutralize reducing substances. But for either method, in small amounts, you always would work from the outside of the spill inward. Don't start from the interior and work your way outward. You'll just spread it more. And then after you're done, you just got to make sure that the pH of whatever was spilled is near or around 7, which is your neutral. And then you can restore the area now back to its use. So all traces must be cleaned up and the area should be neutralized. And of course, dispose anything that you use to clean up the mess in accordance to the local laws and or the call EH&S, and they'll be there. So a good procedure to use when you're in the lab is clean glassware before you use it. So before you make an etchant, you have no idea. And this is why I say, it's always good to clean up after yourself. but and handle everything with care. You don't know if the previous lab, employees or students or technicians cleaned the glassware. So if you were to pour a chemical into glassware to, let's say, make an etchant, it might, if they didn't clean it properly, you don't know if it's something that would react to the chemicals that you are now going to be working with. So those residues can be harmful. A lot of the times they can smoke, they can create fumes that are noxious, and in that case, you can pass out, you can have dizziness, you get dizzy, you faint, you hit your head. Now we're having a whole big issue. And the more injuries that are in your laboratory, the less likely that lab is going to be open. Okay, so definitely taking safety precautions. It's just good practice to clean glassware before you use it. This one really isn't meant for you guys, but it's just good practice if you are ever in a situation where you are the ones disposing of chemical containers that store lab waste. That's your triple wash and thoroughly drying any of those containers. You triple wash them, neutralize them, and that way, once again, when you go to refill it, you're not having the reactions of something that of when you start pouring another acid in. PPE is not a good substitute for good laboratory practice. Okay, so all because you're wearing gloves doesn't mean that you're on the up and up with being safe. You're protecting your hands, but what's on the outside of your gloves could be potentially hazardous to somebody else who's not wearing gloves. Maybe somebody just entered the lab, and even though they haven't done work, they haven't put gloves on, they might touch a light switch, go straight to a microscope. So what's nice about our lab, we have a set of nitrile gloves that are utilized for any of the metallographic and preparation and chemical use for etchants. Then in the microscopy lab, we have a separate, different type of glove that's used for the operation of the microscopes. And either way, if you are planning on using your gloves, it's always good to wash the outside of your gloves, like if you're going to be moving sample to sample, or when you're done, obviously the best option is going to be just to discard them. Okay. And actually EH&S has a video on how you properly take gloves off of your hands. So general PPE rules. This is going to be happening in our labs. So when we do meet, obviously everybody's going to have safety glasses, safety goggles. There's a difference between the two of them, and it's going to depend on what you work with. Using the correct gloves for the job, and replacing them when they become damaged, or if you notice a hole in them or anything along those lines. Wearing actual sturdy shoes. Obviously no sandals. It's winter time right now. I don't think anybody's going to be showing up in sandals, but open toes or any type of perforated shoe will not be allowed in the laboratory. Wearing long sleeve clothing that covers your skin. Obviously we have lab coats that you can wear if you do show up in a short sleeve. Tank top, stuff like that is a no-go when you're in the lab. And the use of respirators when required. So if you are going to be using something that is extremely fumy and potentially dangerous for that can cause any type of upper respiratory issues, then you would use a respirator. You won't need to worry about that in this class. Here's a couple indexes. I'll just kind of leave it here for a couple seconds so everybody can kind of see. If I were to say, oh, this is going to be a PPE index of C, then everybody knows that they will be wearing eyeglass, gloves, and an apron. Looking at these right now, I'm kind of looking at the A, B, and C are probably your the PPP indexes that we will be using in the lab. We're not going to go as far as using any type of respirators or full body suits, boots and gloves. We're not working with any type of nuclear or radioactive materials. So a good procedure, safety glasses must be worn at all times, regardless of what you're doing in the laboratory. You never know what element of danger may be nearby. If you're in the lab and you're not wearing your glasses and somebody else is doing work in the laboratory, you never know how careless they can be. You never know when they might have an accident, and chances are you might be in that path. Which, of course, when we get into the labs, I'll explain a little bit more on a couple experiences I've shared in my time where somebody could have lost their eye. So, gloves, of course, depending on the type of tasks that are being performed, nitrile gloves are predominantly going to be your go-to in this case. I think 7 millimeter, 5 to 7 millimeter nitrile gloves, which are great for handling acids, bases, and making etchants, and using for your metallographic preparation. If you were doing anything else, hot acid etching, which you're not, heat treating or cryogenic applications, you'll have a different set of gloves to wear. But as mentioned previously, the two types of gloves you'll be using are two variations of nitrile gloves. One's for the chemical etching aspects of it, and then the other one is for using the microscopes just to protect your fingers in case anybody else was not practicing good safety etiquette. Lab coats. If you love your clothes, you'll wear lab coats. They are useful for protecting your clothing. It's good if you have your own lab coat because it's designed for your fit. We don't have a one-size-fits-all type deal. When macro etching, it also helps to protect yourself using a rubberized apron, which is resistant to acids. And but you're not going to have to really worry about that. Like I said, these are just tidbits of information I just want to share with you. So lab safety, good fume hoods and good eye wash stations. Good fume hood, that helps protect you from any of the reactions that chemicals may have. Of course, you see that guy right there is not exactly wearing a long sleeve shirt, so that's a no-no, right? The eye wash station has to be flowing periodically. And what's nice about the eye wash and shower stations in our lab is the fact that they are tested frequently just to make sure we don't have buildup and they work properly. Because once again, you just don't know when there will be an accident that happens. Fume hoods. Well, pretty self-explanatory. They're there to help, remove any of the unpleasant odors, fumes, gases that are going to be produced in the lab. You don't even need to have something react. Just some chemicals have a very strong, unpleasant odor, and which can make you nauseous right away. Some etchants, once you mix, will then have a reactive gas or fume that could come off and be potentially dangerous. So your hood's obviously constructed with material that'll be able to resist corrosion because of the all because you're not spilling acid in a fume hood does not mean that it does not corrode on the inside. Vapors and fumes can be just as corrosive. Obviously, you're not going to have the exhaust be close to an intake of air for the building. Otherwise, you will be poisoning everybody else in the building as well. The velocities in which these fume hoods operate have to be within 80 to 120 feet per minute. That's to just ensure that nothing is escaping the hood, and nothing is just nothing is escaping from the hood face. Let's see. Heating reagents. Chances are we're not going to be heating anything in this class, but obviously in a metallurgical lab with chemicals, it's just best to not have a Bunsen burner because they have open flames. Whenever we do heating of etchants and or cleaning using strong detergents, we typically use hot plates. Safer, doesn't have an open flame. Chemicals and metallography. Yes. Well, chemicals are everything. They're toxic, they're corrosive, they can be flammable, and in some cases explosive. It's best to purchase and store small quantities, especially of the more dangerous ones that you don't feel comfortable making. Flammable solvents are typically must be protected from heat, and they're in metal cabinets that are stored ideally on the floor. So you can purchase or make your etchants, but in the smallest amount. Typical for nitol, we make no more than 100 milliliters. So, and 100 milliliters will etch quite a few samples, and it is safe enough to store in a 2% quantity. When you start approaching 4% and higher, it's not safe to store. You got to store them in proper locations. You don't want to, a benchtop or fume hoods are not going to be acceptable. The benchtop, just because anybody walking by can knock it off. When you're making etchants, a lot of the times some of these bottles can build up pressure, and that pressure can explode. Once again, that's another story I can share of an instance that happened to a colleague of mine. Storing stuff in the fume hood is also unacceptable. We've had a couple explosions happen in the fume hood in the past that have damaged the walls of the fume hood, and because other acids were also victim of being in the fume hood when the explosion of another chemical went off. Some chemicals are required special storage, which means they have to be shielded from direct sunlight, heat, or anything else that might cause them to spontaneously react. Keep an inventory of chemicals. That's a very good way of knowing what you have and what you don't. And then it's always important to write down the date of the purchase when you receive the chemicals you ordered. Unbreakable containers are ideal. It's great when you can drop something and it doesn't shatter all over the floor, especially if it's containing something hazardous. Unfortunately, glass containers are most commonly used. And because of that, they need to be stored on chemical-resistant trays inside fume hoods. I'm sorry, not inside fume hoods, inside cabinets and such, just to prevent them from corroding away anything underneath them. Avoiding spills when you're transporting chemicals between cabinets and the lab area you're working with. Never work alone with hazardous chemicals. Storing only minimal amounts. Storing acids and bases separately. They do react. Never store food in a refrigerator that is used to store chemicals. Yeah, don't bring your lunch and put it in there, and you might end up having an issue later on. And then keep an inventory of your stored chemicals. When it comes to lab equipment, this is what separates our lab from other laboratories. So, and it's going to be because of the equipment that we use. All of our equipment in the lab have standard operating procedures for each one. So if you've never used one before, and even after you go through your training, we do have a standard operating procedure, so that way step-by-step process of how these are working. Sectioning equipment is one of the biggest. We do have 3 sectioning machines in our laboratory. Well, what can happen with sectioning? Well, you can get cuts, you can lose loss of limb, stuff like that. Fortunately for the equipment we have, they have built-in safety features that will not allow you to cut your fingers off, because they will not operate unless the hood is down fully and you push the button. So the moment that hood comes up, if the locking mechanism does not work and you're able to open it, the blade will automatically shut off. So there is not a way that you can cut your hands or anything like that. But where do you get your cuts? It's after you cut a sample. If you cut it hot and you didn't use lubricant, you can burn your hand. Or just some materials, in a sectioning process, you use the wrong blade, you actually have a lot of material smear or sharp edges or burrs, and that's where you can cut your fingers or on those. And yes, every cut has to be documented, just to make sure that you're okay. Looking at the cutoff wheels, we do have 2 wheels that are very similar to the one on your right side, the abrasive floor cutoff wheels. They are used to cut larger samples into smaller pieces. I believe the one that we have fits up to a 16-inch blade, and the smaller of the 2 are 12-inch blades, if I'm not mistaken. Then we have precision saws. We have a very nice precision saw that, when utilized, you can actually program it to cut exactly what you want and then walk away if needed. It has the ability to program, feed rate, cutting speeds, force, and precision, which means you can cut 2-inch wafers, and it's smart enough to take into consideration the thickness of the blade when you're cutting these, let's say, 2-millimeter wafers off of specific materials. Grinding, grinders and dust. Obviously, when you're grinding samples and you're grinding them dry, dust particles are in the air, and then you breathe them in. So that can cause respiratory issues all in itself. That's why grinding of materials such as beryllium, magnesium, lead, manganese, and silver are not going to be permitted in the lab. You can always wet grind. That helps keep the dust down, and it also protects your sample from overheating. That's the #1 thing in sample preparation you do not want to do, is overheat your sample. Do not wear jewelry, ties, or loose fit clothing, just because if something of rotation grabs a hold of any of that, it just spells disaster. If you're going to be wearing a necklace, you can tuck it into your shirt. And of course, you do have the danger of striking your fingers against the edge of a belt, and of course that does cause cuts or abrasions. It happens to the best of us. Hopefully not you guys, even though I think you guys are the best. Just learn from me. Don't do it. Furnaces, though you may not be working with any of these, they are in the lab, so I do bring it to your attention. There might be people in the lab performing quenching techniques and or tempering. So obviously anything hot is going to be designated with hot, or should be designated with hot. You just have to be careful when you see anybody working with our laboratory furnaces. Mounting equipment. This is one of the methods you'll be using to mount samples. This is essentially using pressure and heat, and within about 10-15 minutes you have a sample that's ready for metallographic preparation using the polishing tables. Castable resins, why is this in here? Well, their epoxy partners are carcinogens. Skin contact, can cause, rashes, some small little effects. You have to work with the stuff under the fume hood. Some people have had bad respiratory reactions in the past, and it's caused hospitalization. So once again, that's the purpose of the fume hood. Working with solvents. When solvents are mentioned, you're looking at either waters, alcohols, acetone. The most common alcohols that are used in the lab are methanol, ethanol, propyl alcohol, and glycerol. Trying to think through the semester, you'll really be only exposed to ethanol, acetone, and water. You really don't need to worry about the rest of those, at least for this class. If you happen to be working in an industry that utilizes other chemicals, obviously there's SDS sheets on their proper use and so forth. So looking at alcohols, this is going to be essentially a hydrocarbon group that has a hydroxyl group added to it. Methanol is simplest, and it's a wood alcohol. Ethanol is a grain alcohol, which means you can drink it, but that is going to be forbidden in the labs because we use denatured ethanol, I believe. It's got nauseating additives, I believe, that makes you nauseous if anybody drinks it. But it's a grain alcohol. It's just like Everclear. Ethylene glycol, glycerol are some of the ones that you'll see. Acids. These are the ones that have the hydrogen that yields hydrogen ions. Only in a water solution. You have organic and inorganic acids. Inorganic or mineral acids are like hydrochloric, nitric, perchloric, phosphoric, and sulfuric. They're all highly corrosive and poisonous. And then you have organic acids such as acetic, lactic acid, oxalic acid, picric. Picric will not be used because UTEP does not have picric. I utilize picric here at the lab I work at. So majority of the acids we're going to be using are inorganic. Bases, ammonium hydroxide, sodium hydroxide, potassium hydroxide are the main ones that are widely used in metallography. As you can see, you're like, oh, what harm can a base do to my body? Well, it has piercing odors, minor fire and explosive hazards. Potassium, sodium hydroxides can destroy tissue, cause burns, and they are all very dangerous to your eyes, and the vapors can cause damage to your upper respiratory tract. So, yeah, they can be dangerous. Looking at etchants, obviously there's not just one etchant that's perfect for all materials, so there are hundreds of etchants. They all contain some type of aqueous solution with either a water or alcohol that has an acid or base mixed. Your common etchants are typically, like I said, in small quantities. You will not see etchants really stored in greater than 1,000 milliliters, and they'll be stored in polyethylene. That would be your anything containing hydrofluoric. Everything else can be stored in glass containers, and you have to have them properly labeled. Some etchants have to be made fresh, either because they have a short useful life or because they cannot be safely stored. It's nice to have pressure release caps on stored etchants to help produce the buildup of pressure inside some of these bottles. Enough pressure can shatter glass, and hence an explosion can occur. And if you're nearby, not only do you get hit with shards of glass, but you also have the chance of getting hit with the chemicals that were within that container. When we're mixing reagents, solids are measured by weight, liquids by volume. You need to clean any measuring devices, beakers, and storage bottles before use. All bottles must be labeled. You have to use the highest grade or highest purity reagent for all chemicals. And the mixing order is going to be important. Always use distilled water. Do not use tap or deionized water. Make sure the water's cold. You're not going to make it hot. Some of these acids will create an exothermic reaction. So if you're mixing it already with a hot water, it'll just be that much hotter. And in that case, you can create some issues. When stirring, we have magnetic stirring devices. And you typically start with a solvent, then you add your salts, acids, or bases into for your mixing order. Just case in point, a very common etchant I use is 2% nitol. So here are two incidences where nitol exploded and it injured people around them. One guy was using just a 250 milliliter bottle of 3% nitol. And after 2 years, that is a very long time to store a bottle of nitol. That is not good. But it will change color. And this guy, instead of, taking it upon himself, he just started to mix into mixing it. And what ended up happening is he mixed it all in and put it into that same bottle, not cleaning that bottle, and it had a reaction and it exploded. The other one is a grad student using a computer, was sprayed with nitric acid and glass particles because the waste bottle exploded next to him. So about 2 liters of waste of nitric had accumulated in the bottle, and over a period of 12 to 16 hours, the methanol, which is what you use nitol with, reacted with the nitric, creating enough carbon dioxide to overpressurize the bottle, causing that explosion. So he wasn't even using chemicals. He was just sitting next to the fume hood on his computer, and it injured him. So when it comes to disposing of chemicals, you have to develop a plan for the safe, legal, and ecological ways to dispose them. The only disposal you'll need to do in the lab is whatever you use to etch your sample. We're not asking you to carry out the waste bucket that has 5 liters of basic waste or acidic waste. That's where we call EH&S. They come in and they handle that properly. But you will find out you'll need to do, if you are dumping anything into those containers, you'll need to document what exactly you dumped into each of them. So that way when EH&S picks up the containers, they have an idea of the chemicals that have been mixed into those waste containers. So just disposal wise though, some of these etchants, there are different ways you can dispose of them. Some etchants can be diluted very heavily and just dumped down the drain. Unfortunately, that is not how we do things in the lab. We will typically neutralize the solution, and then we can either put it in a waste container. But I can tell you right now, and this is something that I'll get to when we talk about etchants. I create essentially zero waste when I etch, and that turns out to be very nice. So I'll explain that method with everybody when we get to that point of etchants and working with material. Never put anything that you've exposed to acid without neutralizing it in the trash, because all that stuff goes to the landfill. And once again, you start mixing, just like if you mix the wrong things in the lab, well, this stuff mixes with the wrong stuff in the landfill. It can also cause issues for people that aren't even supposed to be exposed to these chemicals. Emergencies, you need to be prepared. Don't be complacent. Accidents can happen no matter how careful you are. I've had my share of accidents, and that's what I'm going to share with everybody in the laboratory when we get into there to talk. But I've had my share of accidents and stuff like that, and you learn. One of the things that you'll need to know is who to contact and what to do, especially if you're in a lab with somebody and an accident happens to them. You have to know how to treat them. Make sure the small spills can be handled by trained staff, and larger serious spills, you know who to contact for the professionals. We do have fire extinguishers and stuff like that, and know where your exits are just in case it's something that is very hazardous to the area. Contingency plans, just in case anything happens. Make sure you have an evacuation to get out of the building. We'll talk about that when we get into the lab. Prompt first aid is important. Making sure that if you do get something in your eyes, we have the eye wash station, and after 15 minutes water, then you can get your medical help. Ingested chemicals, I'm hoping you're not putting your fingers in your mouth and stuff like that while you're in the lab, but because each chemical is different, you'll need to check the SDS sheets. Inhalation, same thing. Get out, get some fresh air. Don't stay in the area if you start feeling dizzy. Skin, wash the areas immediately. Remove the contaminated clothing. Yes, if a bottle explodes and you happen to get it all over your body, we do have a shower, and when you shower, you don't shower with the contaminated clothing on. You will take everything off, shower, dispose of the clothing. It's a case of safety more than it is image. Okay, so if something like that happens, there's no other route. You'll just basically strip down what you can, get all the stuff off, just to save you health-wise, and then we'll get medical help from there. We do have adequate supply of first aid equipment and instructions for use in the laboratory, and we do have spill kits. So your basics for lab safety: you need to minimize all chemical exposures. Never underestimate risk. Use adequate ventilation in the sense of the fume hoods. Pay attention to your exposure limits. Use caution and common sense. Practice good hygiene. And I feel the most important is keep the lab neat and clean, because I feel that with it being neat and clean, you have a much less risk of being able to cause harm in the lab for you and others. So that really concludes the presentation. So what I would like to do is, the assignments have already been posted on Blackboard. The reading assignments are just the documents uploaded pertaining to the OSHA standards and the ASTM standard. There is a syllabus quiz, and of course the website is there to look at the EH&S lab safety training. And equipment training is something that Wayne will send out with information once we get the online confirmation of when labs can be utilized for equipment training. So that now concludes the presentation for week 1. If you have any questions, I'll be in my office hours on Blackboard, and or you can just send me an email. Thank you very much. Good luck with everything, and we'll see you for next presentation.